In this video, we're going to look at a couple of ways of setting up a particular kind of word problem, which involves the relationship between time and the completion of a task when things are working together or a combined effort. So a lot of times, like in word problems, I'm going to read through it, kind of identify some of the key information, but in this particular example, I'm going to organize that information visually with a table. So let me read through it and kind of highlight some of the key information we're going to need later in the problem. So first off, Joe and his apprentice can paint one side of Ye Olde Barn in 3 hours. So I'm going to underline 3 hours. It's going to be key, and that's their combined effort. It took the apprentice alone 8 hours more than Joe to paint one side of the barn. Assuming all the sides are the same, how long would it take the apprentice to paint one side alone? Okay, so let's organize some of this information. I'm going to talk about Joe, I'm going to talk about his apprentice, and I'm going to talk about what they were able to do together. So let's fill in this table. So notice that Joe and his apprentice can paint one side of the barn together in 3 hours. So that's what I'm going to throw here in the together column, 3 hours. And also over here on time, I'm going to go ahead and note the units that it's measured in, which is hours. So using that same reasoning, I'm going to fill in some of the other piece of information that we're given here. The next step, it says it took the apprentice alone 8 hours more than Joe to paint the other side of the barn, and I'm trying to find the amount of time it takes the apprentice to paint one side alone. So I'm going to label the amount of time it takes the apprentice X, because that's what I'm trying to solve for in this question. So in this second sentence, it says that it takes the apprentice 8 hours more than Joe, so the amount of time it takes Joe must be 8 hours less than his apprentice. Okay, so now I have 3 relationships in here, and I want to point something out about this unit of time, how it's measured in hours. Because it's not just some arbitrary amount of hours, it's the amount of hours per the portion of the job completed. It's really how much time it took them to paint one side of this barn. So really the amount of times per barn's painted. Okay, so now I have to somehow combine the amount of work they do. So I want to represent how much work they get done. Okay, but again, it's not just how much work they're getting done, it's how much work they're getting done in a given amount of time. So thinking of it this way, if you notice, if you think about things labeled in the units, time is measured in time per barn painted, and work is measured barns painted per amount of time. So these look like a reciprocal relationship. To further clarify that, let's consider a simple idea. If together it takes them 3 hours to paint one side of the barn, if you think about what that represents as amount of work, they're painting 1/3 of the barn per hour. Because again, if it takes 3 hours to complete the barn, if it takes 3 hours to paint one whole side, they're finishing 1/3 of that side per hour. So just like the units led me to believe, there is a reciprocal relationship between the time and the amount of work that they get done in a given amount of time. So kind of extending that relationship to Joe and his apprentice, the amount of work Joe gets done per hour is the reciprocal of his time, and the same goes for his apprentice. Okay, so now I need to get some relationship here. Now, if you think about what they're doing, they're actually working together to complete this barn. So one way to set up this problem is to think about it's the amount of work per hour that Joe does plus the amount of work per hour of the apprentice would equal the total work per hour. Okay? And all of those variables are represented here. So Joe can complete 1 over x minus 8th sides of the barn per hour, plus the amount that his apprentice can complete per hour would equal the total amount of the barn that they do together per hour, which gives me an equation relating my variable with some numbers, which I should be able to solve. It's a fraction equation. I'll solve by multiplying by the LCD. So I'll need a factor of 3 to cancel out the 3, a factor of x to cancel out the x, and a factor of x minus 8 to cancel out the x minus 8. When I distribute that value across these three terms, this and this, the x minus 8s will reduce, leaving me with 3x. This to this, the x's will cancel, leaving me with 3x minus 24. And this to this, the 3's will reduce, leaving me with x squared minus 8x. Combining like terms, I'll end up with x squared minus, let's see, these will combine to give me 6x, subtracted over will give me 14x, and add the 24 over, and I get plus 24. Is equal to 0. So now here, I want to take a second and think about another way you could have set up this quadratic equation. I'll come back and solve this in a moment, but this isn't the only way you could have arrived at this equation. Another way you could have conceptually thought of this problem might actually be simpler. In fact, I will tell you, you won't even need this together column to think about this the other way. Another way you could have broken this problem down is to think of it as total work divided by time. If I was to multiply this by time, it would just equal the total work completed. Now, I mean, you may look at this and say, well, yeah, that's obvious. Time would just cancel out. But thinking of it this way is conceptually a little bit more creative when you think about how these values are calculated or where they come from. So now the amount of time comes from this 3 hours. That's the amount of time they worked together. So time is going to equal the 3 hours. Now the total work is the combination of their two individual parts. So it's the work that Joe did per unit time plus the amount of work his apprentice did per unit time. That's the total amount of work per unit time, and that should equal the total work. Now the total work is less obvious. You have to think about what they were doing. So what they were doing is painting sides of a barn. So working together in 3 hours, they can paint one side of a barn. So their total work is 1, and technically it's side of barn. Okay, but just notice what happens. If I distribute this 3, I get 3 over x minus 8 plus 3 over x equals 1. And if I do that same transformation I did in the previous example, multiply by its LCD, x times x minus 8, you can verify this for yourself, but after distributing that, you will end up with this exact same quadratic equation. So we have two conceptual methods, or I've given you two conceptual methods for setting up this kind of word problem. So using a table to organize the information, and you now have two ways to conceptually put this problem together. I'm going to focus on this method only because it saves me time in having to fill out this together column. It's not necessary. So now that we've talked about two ways that you can set up the problem, let's actually finish solving it. So I'd go through this by factoring the quadratic equation that I have here. And it factors to x minus 12 times x minus 2. So the two solutions I get are 12 and 2. Now it may look like both of those are valid answers, but we got to go back up here and think about things rationally. If x was 2, it takes the apprentice 2 hours, but then it would take Joe negative 6 hours if you plug in 2. Now that's a problem because negative hours means he's gone back in time to paint this barn. And unless he has a TARDIS, that doesn't seem possible. So what we have to do is reject this value 2 And I get that it takes the apprentice 12 hours to paint a side of the barn on his own. Okay. Let's look at another example. I have two pipes. One pipe can fill an empty tank in 2/3 the time it takes the second pipe to do the same thing. Together, the two pipes can fill the same tank in 12 minutes. How long would it take each pipe individually? Well, just like before, I'm going to use a table to set things up. And I've also labeled these units so that you can still see that reciprocal relationship. Again, labeling these units in your work is not necessary. You can just write time and work, but I'm putting them here for you to see the relationship a little bit more clearly. So now I just called them pipe 1 and pipe 2. Doesn't really matter because we're going to have to find both. So let's say it takes pipe 1 X minutes to fill a tank on its own. It would take the second pipe 2/3 the time, which would be 2x over 3, or 2/3 x. So now again, just like before, if it takes the pipe x minutes to fill the tank, 1 over x of that pipe gets filled per minute, the reciprocal. And just like before, the reciprocal of this would be 3 over 2x. So now I'm going to set it up in that second method. It takes, they're working together for 12 minutes. So 12 minutes times their combined tank filling per minute. So x fills 1 over x of the tank per minute plus the 3 over 2x of the tank that gets filled by the second pipe is the total amount of the pipe that gets filled per unit time times the amount of time should equal the number of tanks filled per minute. So looking up here, how many tanks get filled per minute? Well, it's filling 1 empty tank, so this will equal 1. If it said fill 2 tanks, this number would be 2. 3 tanks, 3, so on. It's how many are getting filled. It's the total amount of work completed. So if I look at this, I can distribute the 12, and I get 12 over x plus, and then 12 divided by 2 is 6, times 3 would be 18 over x equals 1. I'll transform this equation by multiplying by the LCD, which is x. So I get 12 plus 18 equals x, and I get x equals 30. And again, the unit of time here is minutes. So it will take pipe 1 30 minutes, and it will take pipe 2 2 times 30 over 3, which is a common factor of 3, and give me 20 minutes. So it will take the 2 pipes 30 minutes and 20 minutes individually. Okay. Now, one last problem, and this one's a little bit different because they're not working together the whole time. They're working for different amounts of time. But again, I'm going to talk about 2 conceptual ways you can break this problem down. Okay. I'm just going to reveal my table that I've come up with already after having read through this problem, and I'll fill it in as I read through it with you. So in Jacob's spare time, he loves to build rockets. It takes Jacob 12 weeks more than NASA to construct a functioning rocket. He started helping NASA assemble a rocket 2 weeks after NASA started. So together they completed the job 3 weeks later. How long did it take Jacob to build a rocket alone? So I'm looking for how long it takes Jacob to build a rocket. I'm going to let that be x. Now it takes Jacob 12 weeks more than NASA. So the amount of time it takes NASA is 12 weeks less than Jacob. And again, just like before, if it takes Jacob x weeks, then he completes 1 over x of a rocket per week. So that after x weeks, put it all together, you get that amount of time. So NASA, again, also 1 over x minus 12. And I'm going to give you 2 ways to break this problem down. And it's a little tricky. So again, note that NASA is working on this rocket by itself for 2 weeks, and then they're working together for 3 weeks. So there's two parts of this problem. So first, we've got NASA, which working by itself does 1 over x minus 12th of the rocket per week. And they work by themselves for 2 weeks. So that's how much work NASA has gotten done. Again, work done by NASA per week, it's really what that represents, times number of weeks. The weeks would cancel out and give me exactly how much work NASA has done. Okay, so now to that, I'm going to add 3 additional weeks times the total amount of work done per week of their combined relationship. So Jacob and NASA working together would be this relationship. And what this will result in is 1 functioning rocket. An alternative way you could have set this up is to think about what's getting done by each person. NASA works for 2 weeks by itself and then an additional 3 weeks with Jacob. So technically, NASA worked for 5 weeks times the amount of time. So technically, NASA works for 5 weeks times the amount of work it gets done per week would give you the total amount of work it completed. Add to that the amount of time that Jacob worked on the rocket times the amount of work he gets done per week would be the amount of work Jacob contributed to the rocket. And together, that again will result in 1 functioning rocket. Notice that these 2 equations are really the same, because if I have 2 times 1 over x minus 12 and add 3 more of that, it will give me 5 altogether. So they're 2 equivalent equations, both of which are the same. I'm going to work with the second one because it's a little bit easier to work with. So just like before, I'm going to transform this equation by multiplying by its LCD. So that's LCD is x minus 12 times x. I'll distribute that. And over here I'll get 5x plus 3 times x minus 12 equals x times x minus 12, which, when I go through and solve, will give me, I'll combine like terms, I get x squared minus 20x plus 36 equals 0. You can confirm that for yourself by pausing the video, but I'm going to continue assuming it's correct. It looks like it factors to x minus 18 times x minus 2, which gives me 2 solutions, 18 and 2. Now, if you consider the viability of these 2 solutions, if I go back up, 18 would tell me that it takes Jacob 18 weeks and NASA 6 weeks. Now, that's a perfectly valid answer. But if you accept 2, it takes Jacob 2 weeks, it takes NASA negative 10 weeks. And again, just like before, negative time means you're going back in time, which is, of course, impossible, as any NASA engineer will tell you. So you really only get 1 viable solution, which is that it takes Jacob 18 weeks to complete a functioning rocket.